Right. So, hello everybody. I'm Ilarion Melnikov. I'm a new postdoc in the group. I'll also be running the seminars in some technical capacity. So I'm very pleased to have here with us today Ilarion Melnikov, who is coming from Texas A&M and will tell us about his recent work on hybrid conformal field theories. Right. So this is kind of kicking off the official seminar. Next week, Sebastian, who's another new postdoc, will tell us something about gauge fixing somewhere in the details to come. Yes.
Gauge constraint algebra and the fringe float strip.
So, hybrid conformal field theories is the subject, and this is some work that I did recently with Bertolini and Plesser. So Marco Bertolini is a graduate student of Ron and Plesser at Duke, and if you're interested, you can read more about this in the following archive.
Yeah.
Right. So, the focus of this work is a rather classic topic in string theory, in particular in string compactifications, and consists of two-dimensional superconformal field theories with 2-2 type supersymmetry, equal left and right central charges to a particular value of 9, and superconformal field theories with this amount of supersymmetry on the two-dimensional world sheet come with a U1 times U1 chiral symmetry. And with respect to that chiral symmetry, we demand that all of the states in our CFT have integral charges. So this is a domain of perhaps the most simple general class of string compactifications, where we can say that we obtain a nice space-time theory based on an intrinsic CFT world sheet construction. So I'll explain why we're discussing this very classic topic, but let me tell you what are the basic results that we obtained. So the first, which I hope to convey to you today in some detail, is an intrinsic definition of what it means for this CFT to be a hybrid. And I will also maybe mention what it means to be extrinsic versus intrinsic. And the second point is that if we use this type of CFT to obtain a string compactification, how do we obtain some basic information about the space-time theory? And what we can tell you is how to analyze the massless space-time spectrum. Right. So, let me begin with an introduction to just spell out why we're interested and what's the general domain in which we are studying these theories. So the motivation comes from, first and foremost for us, from stringy physics. And what I mean by this is that we would like to have, say, type 2 or heterotic string compactification. And we would like to obtain results that are exact in alpha prime. In other words, we would like to be able to compute quantities in the compactified theory without relying on some sort of alpha prime perturbative expansion. Another motivation comes from a sort of more mathematical physics world, having to do with moduli spaces of conformal field theories versus geometries, concepts like mirror symmetry, and the whole related story. I will not have too much to say about this stuff today. And there are many basic questions that remain mysterious despite these theories, us having some general understanding of these theories for many years. So here are some of my favorite questions, which this work does not maybe answer, but is again, these questions motivate these kinds of studies. So we can ask, can we build a superconformal field theory with these properties without a large radius limit?
What do you mean by without, isn't it?
What do I mean without?
Yeah.
I mean that you have this CFT, in general comes with a moduli space.
Mm-hmm.
Now, in certain situations, in most situations that we know, you have a direction in the moduli space that you can move in and find a limiting locus, which is infinite distance in the moduli space metric, and corresponds to a decompactification limit, where we see that it reduces to, say, a 10-dimensional heterotic string or something like this. And so, does there exist something where you do not have such a limit? We do not know examples of this type.
How much of this list you've made here rely on 2, Could you not ask same questions for some other amount of SUSY?
You could, and I'm very interested in exactly that story. For me, the main modification that I'll be interested in will be to put a 0 there. I'll have a few things to say about that.
Yes. But to begin with, I guess the more symmetry, the better.
Yeah.
For your questions you're posing. Is that the point? Roughly?
Even for, let's say, the way that I build my constructions here, what 2, will allow me to say is that, I'm pretty sure these theories actually exist.
Mm-hmm.
With 0, 2, the situation is much more subtle.
1, 1, 1, 0. I mean, what's special about this? Yeah.
What's special about 2 is, well, many things are special about 2, but let me just say that, to me, the most important structure here is that once you have a 2, you have a holomorphic structure on the world sheet in the theory. Once you have a 2 and a 2, you have a left and a right holomorphic structure, and that gives you a lot of power. And so, actually, I would say that 0, 2 is, say, better than 1, 1, even though 1 plus 1 is 2. Right. So here's one particular question. Before one even gets to such a question, a more basic question is, if we have such a 2-2 theory, it might have deformations that only preserve a smaller amount of supersymmetry, 0, 2. Can we in some way classify this number? Can we compute it in particular constructions? And in general, we don't have a good way of doing that. And if we do compute such a number, then we would want to ask a more general question, which is that if we have a moduli space of 2-2 theories that sits as some special locus in a bigger moduli space of 0-2 theories, well, how does it sit? What kind of space is it? So these are some basic motivational questions, and the point is that we don't have a complete classification of these kinds of theories, and so different ways of constructing the theories give you insights and lead to interrelations between different points in this big space of 2-2 theories. So what are these constructions? Well, the subject is classic, so there are many. Let me begin with the ones that I'm not going to say too much about. So we have various solvable, rational, possibly rational conformal field theories. And these include things like taking a T6, a very nice free theory on the world sheet, and taking some Orbitfold, or more generally, Gepner models. And basically what solvable means here is that if you suffer enough, you can answer any question in the conformal field theory. So you can compute the number of 0-2 deformations. It might be painful in your particular model, but there's a very concrete technique to do it. Another way that we're familiar with doing this is starting with a nonlinear sigma model with a Calabi-Yau target space. And this leads to such a superconformal field theory. And there are many ways in which we might construct Calabi-Yau manifolds. Now, for us to obtain this kind of central charge 9, we're interested in complex threefolds. And, well, one way that's very popular these days and will be relevant for what I'm going to say next is the following. That we can take our Calabi-Yau manifold M to be an elliptic vibration over a complex scalar manifold B. So we have a base manifold, and over every point there is an elliptic curve, a torus. And here's our base. And then we have different tori. And you ask, well, what changes as I fiber? What changes is the complex structure of the torus. So we have some torus with complex structure labeled by a parameter tau1. Then we move along the base, we find some other curve with parameter tau2. And if we move, in order to get a non-trivial vibration of this sort, we're doomed to discover certain singular fibers where tau goes to infinity and the torus pinches.
What is the dimension of B and the dimension of the torus?
Dimension of the torus is 2.
2 real
So this is just a 2 real dimensional one-dimensional complex curve. Dimension of B in this case, of course, would be complex dimension 2 if I want a threefold.
Yeah.
But I can generalize that if I want to make the 9 some other integer.
Sure.
Right. And an important part in this story is that to make this manifold be a nice complex scalar space, as a function over the base manifold, tau varies holomorphically. In fact, it's not really a function, it's a section of an SL2Z bundle. Right.
Which Calabi-Yaus admit this vibration? Do all of them admit this vibration?
No.
What property do I look for?
The properties that you would need to check are certain intersection numbers. So certain intersections of divisors have to have certain positivity properties and certain zeros.
But there are plenty.
There are plenty.
Okay.
Yeah. In fact, there's some very interesting work by Waddy Taylor and collaborators recently, where they point out that if you look in the space of the known Calabi-Yaus, these are, first of all, they fill out a fair bit of it, and second, sort of the whole extreme place, locus, where the H11 and H12 are big, these guys kind of saturate it. Yeah, and maybe one more remark since you asked. So there is actually a very technical result of Mark Prost that says that the topological types of elliptically fibered Calabi-Yau threefolds is finite. So this is one of the sets of Calabi-Yaos for which we can say there's a finite set. In general, we don't know if there's a finite number of Calabi-Yaos yet.
What's
Don't
the
we?
upper limit?
Huh?
What's the upper limit?
There, he doesn't give you a bound.
Well, it doesn't give a number.
No.
5,000?
No, it's not.
But he knows that there must be a number, though.
He
can
knows
prove
that there must be a number.
Mhm.
Yeah. And it relies on a fairly complete classification of surfaces that mathematicians have developed. Okay, so that's another way to build 2-2 CFTs. The third way, which is the one most relevant for me maybe, is via RG flow. So we start with some 2-2 supersymmetric, but not necessarily conformal theory in the ultraviolet, and we let it flow. And if we're lucky, if we've arranged things judiciously, then in the infrared we will find an interesting, non-trivial 2-2 CFT. So the most famous example of this, and the most general example of this that we know of, is the gauge linear sigma model construction. So this is based on asymptotically free gauge theories in 2 dimensions. And as a special case of this, we have what are known as Lando Ginsberg orbifolds.
Before you tell us about that, line number 1, this 2-2 SUSY without conformal symmetry, do you really mean that there is supersymmetry but no conformal version of it? Is that
Yeah.
what you mean? But there is SUSY nonetheless. Okay.
Yeah.
All right. All right.
Right. So Lando Ginsberg orbifolds, which actually, as special cases, realize these Gepner models that I mentioned, one of the solvable CFTs. So how do we build them? Let me start getting a little bit specific. So we start with some representation of 2-dimensional matter, and the relevant one is 2,2 chiral superfields. Phi I, which have some component expansion in the worldsheet superspace coordinates. Let me call them theta L for the left moving and theta right for the right moving. Plus dot dot dot, higher order terms. And we write down a very simple Lagrangian for these theories. So we have an integral over all superspace, so over theta, theta bar on the left movers, theta, theta bar on the right movers, of a free kinetic term for these superfields. And then we write a superpotential coupling. So that's an integral over half of superspace of a superpotential function. So this function, W, will play a key role in everything that follows with some nice homomorphic function. In fact, we want to have it
Is that your deformation?
hmm?
Is that your deformation?
Exactly. If you look at it, you will realize that this superpotential has to have mass dimension 2. So it's a relevant deformation of the free theory close to something.
Preserving 2,2.
Preserving 2,2 by construction.
Okay.
Right. And we will assume that the superpotential satisfies a certain quasi-homogeneity condition. So there exist integers m sub I and n, such that if we rescale the fields with weight t to the m sub I for some non-vanishing complex number, then the superpotential just rescales by an overall coefficient of t to the n. And what this
what's
means?
n? What's
Sorry?
n?
N is an integer, positive integer.
Yeah, but what's the relation to m sub I?
It depends on your superpotential, right?
Okay.
So the point of this is that it'll guarantee for us the existence of these chiral U1 symmetries that we can identify already in the ultraviolet theory. So in general, the superpotential breaks the symmetries that rotate theta left and theta right. But if we have this invariance, then we preserve the chiral symmetry. And the charges of our basic fields are just given by the ratios of these integers, mi over n, which I will denote qi.
What do you mean by UV theory? Do you mean the theory described by the first term alone or both terms? To be specific, what
To
is
be
your
specific,
UV
I
theory?
mean that
Yeah.
if I want to discuss this Lagrangian with this massive coupling, I better tell you what scale I use to specify that Lagrangian. So I fix some scale mu.
Okay.
Then I have a, at scale mu, I have a theory defined by this Lagrangian with this mass parameter m. And then you can see that if mu is much, much larger than m, then this Lagrangian will be more and more free. This coupling will be irrelevant in the UV. And so the free theory is becoming very, very good description. And this perturbation becomes a very good description for mu much higher than this number.
Mu being the RG scale, mu.
Yeah.
Okay. And once you have that the relevant regime, that W term, does it break the SU2 cross SU2 to U1 cross U1 or what?
Sorry, I don't have an SU2 cross SU2.
You never had this, the free theory even doesn't have it.
No.
So what is U1 cross U1 is the symmetry of both terms separately, is it?
So U1 cross U1 is a symmetry which rotates. So let's say U1 left is a symmetry that assigns charge theta left as charge 1, and then the phi i's have these charged qi.
So is it invariant or not, that
Yes.
term?
This-
So both terms are invariant?
Yes.
Okay, thank you.
So we build this UV theory, or rather, this theory was built by Martinek and also by Warner and Baffa in the good old days. And although there is still not a sort of complete rigorous proof, there's just very strong evidence that indeed this theory flows to a superconformal field theory, a 2-2 superconformal field theory, with equal central charges given by a very precise expression in terms of the left and right moving charges, these Q's. And a chiral ring, CC ring. Let me just write it down and then maybe I'll say a word or two what this is. So recall that in these 2-2 superconformal field theories, we have a preferred set, several preferred sets of operators that have very nice non-singular OPs with each other, and where the operator dimension is related in a very simple way to the charge under the U1 left, U1 right symmetry. So this is a particular set of operators. So this is say Q left. Where the weights satisfy this relation. This is the CC ring. And for this Landau-Ginsberg theory, the space of these chiral elements is isomorphic to taking the space of polynomials on the n fields and modding out by the first derivatives of the superpotential. There is another ring that we could build where we take the left weight to be minus the U1 left charge, and the right weight to be still the same. Relation is here. That's the AC ring. And for the Lando-Ginsberg theory, it's very simple. It just consists of the identity. So that's pretty trivial and boring.
Are these phi's the superfield phi's, or deliberately you have something else, like bosonic leading component?
You can make sense of the superspace completion of these chiral ring elements. Here I really mean the bosonic.
The leading component in the capital phi. Okay.
Yeah. That's right. So this is a very nice set of superconformal field theories, but unfortunately, you see we have these q's, which are rational numbers, and in general certainly not integers. So that violates one of my little conditions that I had written down for the kinds of theories I wanted. If you remember, I demanded that my CFT has integral charges.
Why did you want that before?
I'll say in a second. So, we're going to take this Lando-Ginsberg theory and Orbitfold it by the Zn symmetry, which we basically have because of this n, which is a subgroup of the U1 left times U1 right symmetry. And that will achieve for us a projection onto states with now integral charges. A non-trivial AC ring will appear in the twisted sectors of this orbifold. Another consequence is that this Zn orbifold symmetry will lead to a Zn quantum symmetry. So all of the correlation functions in the orbifold theory will carry the Zn symmetry. And now I can finally answer Erion's last question, which is why do I do this? It's because now I can actually apply the standard type 2 or heterotic GSO projections to actually obtain a string vacuum. To obtain a string vacuum where, for example, the candidate gravitino vertex operator will have the right branch cuts with all of the other fields, or with all the other vertex operators in the theory. And
C left and C right is always the same formula, or does it change? Same formula.
for the 2-2 theories, it's always the same.
Whether you orbifold or not, it
No,
doesn't change.
yeah.
But
Yeah. Okay, so that's been pretty abstract, but let me make it a little bit more precise by going through a little example. Don't know my own strength.
what's the amount of space-time SUSY if you get a space-time theory?
If you do type 2, it'll be n equals 2 space-time SUSY.
In 4 dimensions.
If you do heterotic, you'll get n equals 1.
In 40. Okay.
In 40.
Okay.
All right, let's do a little Lando-Ginsberg orbifold example. We'll do the simplest example ever. That's actually interesting. So we'll have 3 fields, phi 1, phi 2, phi 3, and a cubic superpotential. And we'll consider the orbifold, so orbifold, by the obvious Z3 that just rotates all the fields with roots of unity. Okay. So now we have to think about what the superpotential gives us. So first of all, I didn't say this before, but here 3 is the integer 3. if you can't read my handwriting, this psi is a parameter. So a complex parameter that gives us a family of the superpotential. And not everybody in the family is good. So we have this important criterion, which I'll call compactness. And the way to think about this is as follows. So pretend for a second that we just turn off the superpotential. Then we find ourselves with this free theory. And the free theory has this bad property that it's non-compact in particular, right? The fields can propagate all the way to infinity in field space. Those configurations are important. That's why free fields have these logarithmic propagators in 2 dimensions. And so this theory with the superpotential 0 is in some sense ill-defined.
I don't know why they have to be non-compact. I'm sorry. I mean, if your target is a torus, I could declare even in the field theory the coordinates to be those of a
But
torus.
mine is not a torus. My field space is Cn with the superpotential on top. And if it was a torus, then I might have a problem writing a superpotential on it.
Okay.
Right. So this theory has a little bit of a problem, but if we do allow ourselves a superpotential, then there is a scalar potential for the fields, which is proportional to the first derivatives of the superpotential squared, and that prevents the field from exploring all of the infinity of Cn, and gives us an effectively compact target space. And we will say that the superpotential is non-singular if and only if solving these equations, dw equals to 0, gives us the unique point, which is the origin in Cn. And so, for example, if you play with this superpotential, you will find yourself that if psi happens to be the cube root of unity, then you will be able to solve the dw equations, dw equals to 0, on a whole line in C3. And so, in our parameter space, psi cubed equals to 1 is the singular locus. By contrast, psi equals to 0 is what gives us a Gepner model. Okay, well, we can now apply to that superpotential the formula that we have for the central charges. And what do we find? So we find that the central charge is now just 3. There's one marginal CC operator. In fact, it precisely corresponds to this parameter psi, so our ability to choose any psi in that superpotential and vary it gives us this one-dimensional family of deformations. And we also find there's one marginal AC ring element that lives in the twisted sector. And if you think about it for a moment, then if you've thought about string compactifications, you know a theory that does this. In fact, this CFT is isomorphic to a very well-known CFT, which is just the nonlinear sigma model on T2, the 2-2 supersymmetric nonlinear sigma model on T2, which in particular we can realize as a vanishing of the hypersurface, the same hypersurface W as I've written there, inside CP2 with coordinates phi 1, phi 2, phi 3. Okay, well,
Is there a geometry we can read off by the knowledge of W? I mean,
Whether there is a corresponding geometry?
some metric or something. I mean, these properties of compactness, singularity, and so on. Can we make them more concrete by constructing a metric or something
So,
in the field space?
In field space, I would say that you should really think just you should think in the CN metric, but then just think to yourself that you have this weighting factor in e to the minus s, right? So those configurations they're there, but they're just exponentially suppressed.
Yeah. Okay.
Okay, so the message here is that I used a Lando Ginsberg theory to build a superconformal field theory that's actually also has a representation in terms of a geometry. And this is an example of a very general phenomenon known as the Calabi-Yau Lando-Ginsberg Orbitfold correspondence. So what this is essentially we have some moduli space of theories. So this is the AC moduli space associated to some Calabi-Yau, and it might have some large radius limit where the Calabi-Yau becomes big and really describes the physics very well. But there might also be a point somewhere deep in the interior of this moduli space where the Calabi-Yau is very tight and small, where we obtain a Lando-Ginsberg Orbitfold theory. And the reason that I tell you this is because it now completely indicates the inevitability of what I will call hybrids. So let's go back to our Calabi-Yau here. We have this nice elliptically fibered Calabi-Yau. And let's assume that we have a way of moving in the moduli space of this geometry where we keep the base fixed while sending the torus to a very, very small size. If we do that, then we expect that we should be able to, by taking the limit properly, really obtain a description where the torus can be just as well described by our superpotential Lando-Ginsberg model. So what it tells you is that if you believe in elliptically fibered Calabi-Yaus, and say K3 fibered Calabi-Yaus, that's another generalization of the idea, then it's very natural to think of hybrid theories where what you're doing is you're fibering a Lando-Ginsberg theory over a base geometry. And that is what a hybrid really is.
In what sense it's hybrid though? I mean, hybrid usually means two different features or
yes.
regimes. What are they here?
The way I think of it is this, that when we construct massless CFTs in 2 dimensions, we have 2 very concrete things built into our heads. One is you write down a model where you have degrees of freedom interacting by some superpotential that's higher than quadratic. 2 is you write a nonlinear sigma model. In this case, what the hybrid is doing is you have some degrees of freedom that are interacting as a nonlinear sigma model. In other words, the field's parametrizing this base geometry B. Then you have other fields that are interacting with a superpotential, right? And then the process of hybridization is how do you bring them together consistently. Hybrid is one of these words like generalized that's just abused and horribly treated, but what can you do? Okay, so let me just then write down that superconformal field theories for elliptic or K3 fibered Calabi-Yaus over a base taken at small fiber volumes tells us that we can model the theory in the UV as a Lando-Ginsberg model fibered over a Kähler base B. Now, this is a way of thinking about hybrids, of coming to it from sort of combining the two pictures of Lando-Ginsberg and geometry. It's not how actually they first appeared. They appeared when people were studying gauge linear sigma model constructions in some generality. This is work of Witten and also Aspinwall, Green, Morrison, 93, 94. And what they had was a moduli space of these two-dimensional gauge theories with the parameters that they could tune. And by going to different parameters, values, you would discover, in this region, this gauge linear sigma model gives me a nice Calabi-Yau geometry. In this region, if I tune it differently, it gives me a nice Lando-Ginsberg Orbitfold. But what happens if I go to some other regions? And what they found is that in general, the answer is this structure of a hybrid. So the message is that hybrids are very, very common in the way that we build two-dimensional CFDs, but we don't know too much about their structure. So that brings me to the second part of the talk, which is an intrinsic definition of what a hybrid is, without relying on any gauge linear sigma model embedding or anything like that.
So far in what you told us, there was no gauging at all.
Yeah. Well, I would say that actually the gauging of the Lando-Ginsberg theory to get an Orbitfold, that's a gauging. It's in that sense that a Lando-Ginsberg Orbitfold is a trivial example of a gauge linear sigma model.
What is being gauged? Is it a continuous symmetry?
In the Lando-Ginsberg Orbitfold, it's discrete symmetry.
Discrete symmetry?
Yeah.
Ah, I see.
Like the Z3 of the torus. Okay.
So it's not the U1 plus U1?
No. Yeah.
Okay.
If you do that, then you have to
Lose
get the
everything.
world sheet supergravity, right? If you start gauging the R symmetry. So, no, we don't want to do that yet. Okay, so let's say some things about what these discrete hybrids are. What these intrinsic hybrids are. Can anybody still read the blackboard with all the background? I don't know. I'm finding it hard. So we start with a gauge linear sigma model, which is a 2-2 nonlinear sigma model with some Kähler target space Y0. And on this space, we of course obtain, it comes with a Kähler metric. And now to build a hybrid, we would like to put a superpotential, right? So some function, some holomorphic function from this space Y0 to complex numbers. And here we of course immediately meet the constraint that the superpotential has to be trivial, or our manifold Y0 has to be non-compact. Right? Because holomorphic functions on compact manifolds are fairly few. But if we pick this kind of non-compact Y, fine, we can possibly find a superpotential. And then we will have a term in the action, which is just the square of the superpotential measured in this metric, the Kähler metric, which will again act to cut off the infinities of this non-compact manifold. So we'll restrict this to a compact set. And we will say that the potential condition on such a theory means that if we look at where the superpotential is trying to localize us, it's given by a geometry B, which is a smooth, compact submanifold of dimension D of Y0. And now again we're in a situation where there's lots of field space in the non-compact direction of this Y0, which is irrelevant to the infrared physics because it all gets suppressed by this huge potential. So we can concentrate, if we are interested in the low energy physics, on just what the fields are doing near this base geometry B. And what that means is that we can model in IR by what I will call Y, which is the total space of a vector bundle. So just locally a trivial structure over the base B. And so this X is a holomorphic rank n bundle. And now if we pick local coordinates, U to be coordinates on B, and these phi's to be the coordinates on the fibers in the x directions, then our superpotential is given by a sum of terms where we have these various monomials that we construct from the phi i's, and we take the coefficients valued in the base. And we demand that this is a nice holomorphic, globally defined object, meaning it's a section of the trivial bundle over Y. And then, since the phi's here are various sections of this holomorphic bundle, then the coefficients have to be sections of the dual bundle. And the simplest case of this kind of construction is just where you take this vector bundle to be a sum of line bundles. That's the case that we really analyzed in detail. Okay, so the relevant geometry is a bundle over a Kähler base and a superpotential function satisfying this property. Now, just as in the Lando-Ginsberg case, it's crucial that we preserve certain symmetries, in particular these U1 left times U1 right symmetries, in order to be able to say something about the infrared physics based on this geometry. So in the W equals to 0 theory, this is very easily done, where we simply assign charges to the superspace coordinates on the world sheet, and we keep the y's completely invariant, the bosonic y's invariant. And this will be a nice symmetry of our theory. However, even if this is a nice symmetry, it can have a quantum anomaly. And in order for it to be anomaly-free, we need the first Chern class of the manifold Y to be 0. Now, we will actually work with we worked with a slightly stronger statement, which is that Y is a non-compact Calabi-Yau manifold. Okay, so this is what happens in the W equals to 0 theory. But in addition to these U1 left and U1 right, there are actually a lot of symmetries where we simply rotate the phases of all of these different fiber fields. And that's sort of giving us too much symmetry. But of course, as you might guess, something else happens when we consider non-trivial W. So generic W breaks these symmetries. But we can preserve something, and preserve as much as we need, if we assume that there exists a unique killing vector, V, a holomorphic killing vector, on our manifold Y, such that when we take the Lie derivative of our superpotential, just gives back the superpotential. So this is the analog in hybrid land of that quasi-homogeneity condition that we wrote in the Lando-Ginsberg theory. And in this case, we really preserve the nice U1 left and U1 right symmetries that we're after. And at this point, I can pause and maybe point out that this construction has two natural limits. One limit is where we take the base manifold and we declare it's a point. That gives us back a Lando-Ginsberg theory. The other limit is where we declare that the superpotential is 0. If the superpotential is 0, then this potential condition implies that our manifold B is actually the whole manifold Y. So it's therefore Y is compact and Y is Calabi-Yau. So the hybrid world sort of interpolates between Lando-Ginsberg and Calabi-Yau in a slightly different way than other interpolations.
So it's not fully geometric model.
Exactly. That's its beauty, is that it gives us a place where we can play with these non-geometric backgrounds.
We don't know much about low energy limits of such non-geometric models, do we? Eventually, if somebody wants to, do some low energy analysis, how difficult is it?
Well, it depends. So, for example, it depends on what kind of question you might want to ask.
Let's say 1, 0 heterotic case where I want to know Yukawa couplings.
1, 0.
Yeah. Sorry.
2,
N
0.
is 1. N is 1.
Okay, so 2, 0 in general, it's murky. 2, 2, which still preserves n equals 1, can compute lots of Yukawa couplings exactly.
Even if there's no geometry.
Even if there's, yeah, at the Lando-Ginsberg Orbitfold point, no problem.
Okay.
Yeah. Yeah, this is why I like these things, is that you can actually touch these questions and compute, as opposed to just...
You can compute spectrum, for example?
Yes.
Massless
Yes.
fields, massive ones.
Massive's hard.
I see. Okay.
Yeah.
Do you have a sense about the number of things? I mean, it's like what kind of yaws we don't know. Of the finite or infinite. How about if you generalize to your hybrids, can you say it's definitely could be not infinite?
You can definitely you cannot say that it's going to be infinitely many. So
So what's the positive statement? What can you say?
My guess is that so there's a beautiful work of like Kreutzer and Skarka that classifies Lando-Ginsberg orbifolds fairly completely. And my guess is that here you probably can run a very similar argument, and if you combine it with the classification of surfaces that you know, you might actually be able to have a fairly complete understanding of how big this set is. You might be able to classify it.
Finite or?
It's a total guess, I'm shooting in the dark, but I would guess it's finite. Yeah, it would be very exciting to find an infinite set of string back theory. Okay, so I'm running a little bit short on time, so let me just make a few important points. So perhaps the most important technical point that I need to state is that not every hybrid is good. So here is a technical definition of what good is, finally, for those of you who have been wondering. So for good hybrid, that killing vector V is a vertical vector field. In other words, it only acts on the x directions, on the bundle directions, and does not move the base. And it's in this case that we're really very certain that this description of a fiber at Lando Ginsberg over a base is a good description. More generally, one finds these pseudo-hybrids, as they've been named. The name comes from work of Aspinwall and Plesser a couple of years ago. There we're not sure. It might be actually that pseudo-hybrids are ill-defined conformal field theories. In other words, they're singular. So you try to compute correlators, you try to compute spectrum, and you get infinity all the time. The state of these is, let's say, under investigation. Okay. And finally, section 3, in view of time, will be very brief. So, hybrid limit and massless erotic spectrum. So now what we're thinking about is that, first of all, we do our Orbitfold by Zn, as we did in Lando Ginsberg case, to obtain a nice GSO projection. And we study the various string vacua that we can obtain. So what we can do is we can compute the massless heterotic spectrum in what we call the hybrid limit. Hybrid limit means volume of the base manifold to infinity. And let me just end by comparing this with other ways that we know how to compute spectra. Okay, so if we have a Calabi-Yau geometry and a 2-2 CFT that follows it, we write down the spectrum. And it's given by at least the number of massless neutral, gauge neutral singlets is given by a sum of the two Hodge numbers of the Calabi-Yau, so H11 plus H12, plus the dimension of a cohomology group with coefficients in the endomorphisms of the tangent bundle. And in this case, these numbers here are protected deformations. In other words, quantum corrections, as we move away from the large radius limit, will always leave these guys massless. These, however, can and do jump, and there are worldsheet instantons that can lift some of these classically massless degrees of freedom in the space-time theory. So basically, this is true plus world-sheet instanton corrections, which correct this case. Then in Lando Ginsberg Orbitfold case, we actually know the exact spectrum due to work of Kuchner and Witten. And now you can see that again the hybrid is a sort of intermediate case. So what's happening in the hybrid is my spectrum is exact up to the world-sheet instantons that live in the base manifold B, right? And so then if I have a model with a big moduli space that, let's say, has a large radius limit point, has a Lando Ginsberg Orbitfold point, and say some hybrids, I can now really effectively compare the different numbers that I compute and try to see what kind of masses are generated by world-sheet instantons. So that's one very specific application of this kind of technology. And more generally, you can think of it as a very nice laboratory for understanding these world-sheet instanton corrections. So even though we know they're there is no direct computation of such a mass that's ever been done in a Calabi-Yau, because the computation is very difficult, basically because the number of world-sheet instantons in a Calabi-Yau is very non-trivial. But now if I take a base that's very, very simple, say a P1, suddenly the problem can become much more tractable. So that's one another sort of technical.
So how does this relate to your original motivational comment, where you said that you want two all orders in alpha prime results? Is this where that comes in? You mean you can derive such results because of this hybrid regime?
I can derive constraints. So maybe I cannot. This does not enable me to compute anything like the full superpotential, but I can find some constraints that that tell me that here's a very simple kind of example. So suppose I have a one-dimensional parameter space. So here I have a Calabi-Yau, here I have a hybrid. Okay, and I compute in the Calabi-Yau regime, I compute some n, which is this number of singlets here, of these kinds. I do my hybrid computation, and I come and I find the same n. This is pretty good evidence that there's not a superpotential that lifts these directions. So such constraints. They're very basic, but on the other hand, they're as good as what we got. So there are many extensions of this. I'm currently very interested in the 0-2 version of this hybrid geometry, where you equip this structure with an extra bundle. Yeah, this is one of the directions that I'm investigating, and if you're interested, I would be happy to talk about it more. And I'm done. Sorry for going over. I think somebody should ask a question
questions
before Eric.
People will hate me though. That's the price I pay.
No, we don't hate.
I generate hatred, but I'll ask you one question at least. What is the general philosophy behind the study of superstring macro? I'm asking as a philosophical, the big picture kind of, what is nowadays, in 2013, if someone is working on string macro, what are the hot button issues, what is the philosophy?
Well, so here's a sort of basic paradox. That you talk to model building people, and they say, I have 3 trillion standard models right here constructed. And you ask them, okay, that's really cool. How many massless neutral fields do these models have? And they will hem and haw, and then they'll say, well, lots. And they'll say, well, is there a problem with that? And they'll say, well, but it's an n=1 theory, so there's a superpotential. And generically, n=1 superpotential will lift everything that is not protected by.
Become massive and forget
Everything's
about
gone, right? So it's great. The problem though is if you buy that, then the other thing that you should buy is that also maybe an n equals 1 superpotential will generically break supersymmetry. So which supersymmetric vacuum is being discussed? And I think this is a crucial issue to understand. What kind of superpotentials, what kind of constraints on the low energy physics come beyond just declaring that you have an effective field theory, where all you really know is, from string theory, you read off some gauge charge sector. That's usually fairly easy. But you have no idea what's happening to the moduli. For example, is there a potential that simply decompactifies your Calabi-Yau back to 10 dimensions? So that what you thought as a compactification is actually just...
So are you saying that non-perturbative effects are not well understood?
Not well understood
what
at all.
What you are doing, you are aiming at, is to have a handle on non-perturbative
Yes.
effects.
And so my philosophy is that if we want to talk about string vacua, we need to address those questions. Now, this is, of course, this has a big elephant in the closet, which is the string non-perturbative effects. Do I have anything to say here? Nothing. I'm doing perturbative heterotic string. But on the other hand, at least I can get alpha prime, I can get exact results. I think developing these techniques and then maybe trying to use various dual descriptions to try to corner the answer is an important way forward. And I know this sounds very dated, but to me, before understanding such things, naming numbers like 10 to the 500 is a little bit, 10 to the 500 times 0 is still 0. So, yeah, that's my philosophy.
Okay. It's unfinished business.
Yeah.
In other words. Okay.
Yeah. And there's also a lot of beautiful mathematics hiding there,
Sure.
which is a whole other story.
Sure.
Any other questions, concerns? All right, well, thank you very much. And next week, remember, Sebastian?